So Monday, we learned how to do the exponential rule. Tuesday, we learned how to do the logarithmic rule. And today is a technique called logarithmic differentiation, which combines the two rules at the same time. We use both of the rules. So let's review when we use the first two rules, and then we can figure out when we would use this last one. You've seen a slide like this before. If you're asked to find the derivative of y equals 4 to the third, the truth is that 4 and 3 are both constant numbers. So what rule would I use? I use the constant rule. And the constant rule tells me that y prime is 0. I use that when everything about the values are constant. The next part of it's constant and part of it is variable. Where is the constant in the second function? Okay, the constant is the number 3, and that is the power. So since the constant is the power, then we use the power rule. It all depends on where the constant is. If everything is a constant, you use the constant rule. If part of it is a constant, you look at where the constant is, and if the constant is part of the power, then we use the power rule. So y prime would be 3x squared. Our third option, we see, okay, part of it is a constant again, but the constant is down as part of the base. And so in that case, we use the exponential rule, which is what we learned Monday. And we have y prime equals 4 to the x times the natural log of 4 times the chain rule of 1, which we could simplify to being 2 ln 2 times 4 to the x. Sometimes they'll put the 2 ln 2 in parentheses. All right, what wrinkle do we encounter in our very last function? There's no constants. Nothing about it is constant. Okay, so remember, in the first one, everything was constant. In the second and the third, part of it was constant and part of it was variable. But in this last option, there's nothing about it that is constant at all. There's a variable in the base and there's a second variable in the numerator. And so this needs a new technique of integration called logarithmic differentiation. It's a two-step it's a three-step process, but the first two steps are inherent in the words logarithm and derivative. And so if you can remember the order of that's the order in which you do it. It's a three-step process, but the first two steps are apply a logarithm and then apply a derivative. So let me show you how that works. Here. Okay, here's where we're at. The process of introducing logarithms before differentiating. Okay, logarithm first, differentiating second. The situation is when neither the base nor the power is constant. All right, that is the main situation where you're going to use this technique. You can also use this technique as an alternate to the quotient rule. So if you're looking at it and the question and you're like, oh, that quotient rule is going to be really hairy scary. Okay, it's just going to have so many subtractions and squares, and it's just going to look like a mess. This technique is a different way of attacking a quotient rule, and it actually works out much simpler. Okay. Now, sometimes the quotient rule works out simply enough in itself, but if the quotient rule looks like it's going to be a beast, then maybe this one is going to be the best way. So we'll do some of each as samples. All right, first, let's look at, here's a situation where neither the base nor the power contains a constant of any kind. The base is the variable x, the power is the function cosine of x, and so this would be a classic example where logarithmic differentiation is going to be the best. All right, so step one, use a logarithm, but use it on both sides. And so the logarithm you always want to use is the natural logarithm. In calculus, it's always the natural log as are going to be our default. If I introduce a logarithm to the left side of the question around y, I would also need to introduce a logarithm to the right side around x to the cosine of x. By doing that, I invoke a property of logarithm that's going to be really helpful to me. Hey, what property do I get to use now that I've invoked logarithms? Bring it to the front. Okay, bring the cosine out to the front. Okay, that's not a derivative, that's just a property of logarithms. So now I'll have the logarithm of y and the cosine of x times the logarithm, and the logarithm is just around the x now. That's the first step in the process, is bring in the logarithm and do it on both sides. The second step is bring in the derivative rules you need and do them on both sides. There need to be derivative rules on both sides of this problem. On this side, the derivative rule I'm going to use is the log rule, because that's all I've got is the log of y, the natural log of y. On the other side, what rule will I need to use? Product. So you're going to use different rules on different sides, but you just, whatever it is, you got to do the derivatives, appropriate derivative rules on both sides. Okay, let's start with the left, because that's the easier side. The log rule says 1 over y ln e times the derivative of y, which is dy dx. That's the log rule. The quotient, 1 over the thing in parentheses, times ln e, times the derivative of the thing in parentheses, which is dy dx. So that is the log rule on the left. On the right side, I'm going to need the product rule. The product rule will start launching me with the second half of the product, which is the natural log of x, times the derivative of the first part of the product rule, which is negative sine of x. And then I will add to it cosine, and then follow it with the final derivative, which is 1 over x ln e times dx dx, which is going to be 1. So look at on one side, on the left side, I have 1 over y ln e dy dx. On the right side, I ended up with 1 over x ln e dx dx. Now let's just simplify. Clean it up. Both of my natural logs of e will become 1, so that will simplify. My dx dx also becomes 1, so that will simplify. So I'll be left with 1 over y times dy dx equals, and then just to clean this up, I'll have negative sine x times the natural log of x plus the cosine of x. Okay, that's what I've got so far. Sorry, yes, over the denominator x. Thank you. I forgot my denominator. Okay. Have I answered the question? Let's go back to the first 2 words of the problem. What is the problem asking me to find? Find dy dx. Do you see dy dx? Okay. I'm supposed to find dy dx, which means get dy dx by itself. So what would you do to both sides of the problem to get that dy dx alone? Multiply by y. So dy dx by itself would end up to be y times all of this okay, so y multiplied. I just multiplied both sides by y, so y goes on the other side. And what was y in the first place? Y is defined as x to the cos x. So just erase it and make it x to the cos x times all of that. And you're done, because you just got dy dx alone. You do not need to distribute. You do not need to do more simplifying. You can just leave it like that with the thing multiplied out in front. I mean, if you want to spend your time distributing, you can, but you don't have to. So it's 3 steps. Logarithm first, both sides. Differentiate second, apply whatever derivative rules you need, and then get dy dx alone so that you can answer the question as your final step. So let's try that again. Here is another opportunity where we get to use logarithmic differentiation because although there is a constant, for number 3, it's attached to an x, which is a variable. And so as long as the base part, which is in parentheses, contains some variable, it's not a true constant. It's 3 times the constant, or the constant times 3, and then the square root. So this would be a chance for you to do logarithmic differentiation again. So just following the rules, we're going to introduce a natural log on the left side, and we will introduce a natural log on the right side. And the natural consequence of that is that you get to pull the square root of x down to the front. So that would be the automatic natural consequence. So we'll have ln y equals the square root of x times the natural log of 3x. You might want to pre-write this and not write the square root of x. You might want to pre-write it as the quantity x to the half, just for your own personal benefit for when you're ready to do the derivative rules. Then you're ready to invoke differentiation. You'll invoke the log rule on the left and the product rule on the right again. So the log rule on the left is going to tell me 1 over y Lenny times dy dx. The product rule on the right will give me the natural log of 3x times the derivative of x to the half, which becomes x to the negative half times half. Plus x to the half. And then the derivative of the natural log portion of it, which will be 1 over 3x times Lenny, and the derivative of that, which is 3. Then you'll want to simplify all your Lennies and simplify anything else that can be reducible. So my natural logs of e are simply 1. So I'll have 1 over y times dy dx. Then I'll have the natural log of 3x over the denominator 2 rad x. So that's just simplifying, getting your denominator down to the bottom, bless you. And then the second one also has a numerator and denominator. The numerator will be rad x and the denominator will be plain x. And then you just need to get dy dx alone. So the other side would become y times all of this. And then just change your y to what y represented. And y was the quantity of 3x times the square root of x times all of that. Do not need to simplify, do not need to distribute. You can just leave it like that. Are there any questions about these two situations of logarithmic differentiation? You can recognize it. Your homework does sneak in some ones that don't need logarithmic differentiation, just to keep you on your toes. So you don't need logarithmic differentiation for all of them, but most of them. Okay, the last one would be, let's skip that one. Let's do the quotient one. This would be the same. Apply your logarithm rules and differentiation rules. Yeah?
Sometimes this is easier than the quotient rule.
Yeah, I'm going to do one right now. Okay, so here is where we certainly could use the quotient rule. The quotient rule here would, we'd end up, but what would be embedded within the quotient rule because of what the denominator looks like? Yeah, you'd have to be, not only are you doing the quotient rule, but as you do the quotient rule, you have to remember to do the product rule as well. It's possible, it's doable. But I'm going to just propose that maybe we want to think about doing logarithmic differentiation instead. So if we do logarithmic differentiation, you would have ln around the y, and you'd have ln around the numerator and the denominator. And there is a property of logarithms, just like we were using the property that allowed us to pull powers to the front. There's a property of logarithms that allows you to separate numerators and denominators. And so the property is, if I want to separate, I use subtraction. Do you remember that property? It's minus the natural log of x, and I can separate the cosine x as well. Why both of them? Because they're both in the denominator. So anything in the denominator is part of the subtraction. Anything in the numerator would be part of the addition. So this is the logarithmic step. The next part is the differentiation step, which means you're going to apply the log rule to every piece, because every piece is a log. So it'll be 1 over y len dy dx. It'll be 1 over x plus 5 len times 1 minus 1 over x len times 1 minus 1 over cos x len times negative sine x. So this allows you to avoid the quotient rule and just use the logarithm rule all the way across. So all my lennies will be 1, of course. So I'll have 1 over x plus 5 minus 1 over x. The last term is interesting. Is the last term going to be addition or subtraction? Addition. And what will the numerator be? Sine. And what will the denominator be? Cosine, which could also be written as tangent x. And then I want to get dy dx alone. So you can kind of do a bunch of things at the same time. If I want to get dy dx alone, then that means all of that will be multiplied by y. But we know that y was originally x plus 5 over x times cos x. And that gets me dy dx alone. So it's a very different looking answer than a quotient rule answer. But it is legally and legitimately the exact equivalent answer. This will calculate the slope for us just like the quotient rule would calculate the slope for us. So this is an alternate to the quotient rule. Yeah?
Like if this question was on a multiple choice, it would put the answer that way.
The nice thing about the AP exam is they usually announce to you that they want you to use logarithmic differentiation. So they would say, use logarithmic differentiation to find the derivative of blank. So they're very kind about putting it out there. Or they'll say, use logarithmic differentiation to show that the derivative turns out to be this. And they even give you what the derivative is supposed to be, and they just want to check step by step that you know how to get there. So they're very gracious about that. Yeah.
So logarithm that lets us take the fraction and turn it into.
The logarithm part of it, the logarithm rule, allows you to set, that's a property of logarithms.